Hi there, it's Dr. Maxwell, and we're going to be talking about Chapter 8, where we learn how to do some proofs involving sets. And here's what we're going to try to learn. We're going to learn how to prove that some object is an element of a given set. We'll prove how you can show that one set is a subset of another set, and how do we prove set equality. You should review the set theory in Chapter 1 and the notation in that chapter. Now, we will not do all of this chapter. See Canvas for what you should read and which examples you should look at. And just like before, these proofs are going to rely pretty heavily on definitions. So we better make sure that we understand these definitions. Understand the definition of element of, subset of, what is a Cartesian product, union, intersection, set difference, complement, and the power set. So all of those things are important. And here's a bunch of them, and we will go through these just to make sure we remember what they mean. Section 8.1 talks about how we prove something is an element of a set. Basically, you just have to show that it satisfies the definition of that set. So let's make sure we understand what these sets are. So this is the Cartesian product. So if A comma B is an element of A cross B, then what? Well, then A is an element of the set A, and B is an element of the set B. That's what it means. And here is the same definition using X and Y. Now, what about the union? If X is in the union, what does that mean? Well, then X is an element of A, or X is an element of B. And often these kind of proofs will involve cases. Case 1, X is an element of A. Case 2, X is an element of B. And remember, X could be in both. That's always a possibility with the mathematical or, unless specified otherwise. And this says the same thing in a very concise way with symbols, using the or symbol from logic. Okay, this is the intersection. So if some element is in the intersection, what does that mean? So if X is in the intersection, then we know this. Then X is in A and X is in B. Right? And this is the set difference. A minus B. What does this mean? If X belongs to this set, A minus B, well, I can do this. If X is in the set A minus B, then we know X is in A, but X is not an element of B. Okay, complement. What does it mean for an element to be in A complement? Well, if X is an element of A complement, then X is not in A and X is in U. In other words, X is in U, but X is not in A. And here's the power set. Usually we use a capital X for this. If X is an element of the power set of A, then what does that mean? It means X, I'll make it a capital. That's how in script, this is a uppercase X. Sometimes it's hard when you're writing on the board or on a tablet. And this is lowercase, a way to differentiate. So if this is an element of the power set, what does that mean? It means that this is a set that is a subset of A. So hopefully all that made perfect sense to you. We'll use these ideas in the proofs that we do. We're not really going to do an element of proof, but we have done one already. When we proved that the square root of 2 is irrational, we proved that that number is an element of the irrational numbers. And we also proved that the square root of 2 is not an element of the rational numbers. We did both those things. Okay. Now, if you want to prove that one set is a subset of another, we have two approaches outlined here, and we'll look at a third approach too. These types of proof are often called element arguments. And so you may be in another course when someone gives you a hint of how to prove a proposition. They might say, why don't you try an element argument? So you need to know what that means. So what you do to prove that A is a subset of B, you suppose that A is an element of, well, let me say it again. You start by supposing, and I'm going to use X. X is an element of A, and then you show X is an element of B. And X is arbitrary. So what you're showing that for any element in A, X could be any element in A, and if it is, you're showing that it's also an element of B. Now, sometimes we might want to use a contrapositive approach, so you just form the contrapositive. So let's look at this as an if-then statement. So as an if-then statement, I could write if X is an element of A, then X is an element of B. This proves that A is a subset of B. And so the contrapositive, of course, would be if X is not an element of B, then X is not an element of A. And this would prove that A is a subset of B because this is the contrapositive. These are logically equivalent. So let's do one. So prove that if A is a subset of B, then A minus C is a subset of B minus C. Now sometimes I like to draw a picture. What do I mean? A Venn diagram. Because later on we are going to have to be deciding whether things are true or not. And so a Venn diagram can help us. So we need to draw a Venn diagram that represents this situation. we have 3 sets, but it's given that A is a subset of B. So I'm going to draw, call this B, and I'm going to put A inside B. And I want to make this very general, so I'm going to have C overlap both A and B. And then this whole thing is the universal set, right? So now, let's look at what this is saying. We have the setup. A is a subset of B. So let's look at A take away C. Where would that be? I'll shade that here. This is the set A minus B. A minus C, right? Includes everything except for the part in the set C. Okay, what does B minus C look like? Well, that's everything in B that's not in C. So that's all of this. So now ask yourself the question, is A minus C a subset of B minus C? And the way to see the picture is this is in green and this is in blue. And yes, that is a subset. So now let's try to prove it. All right. We are going to start by saying, suppose this is a direct proof. A is a subset of B. Now, this is a little different than what we've done before. I'm going to say, let X be an element of A minus C. And then I'm going to show, this is what I want to show, that X is an element of B take away C. So I just have the definition to work with right now. So I'm going to say what that means. Then X is in A and X is not in C. Okay? Now remember, I want to show that X is in B and X is not in C. So I already have part of my answer there. The other part comes from our supposition, what we assumed. So since A is a subset of B, X in A means X is in B. Therefore, this X is in B and X is not in C. And so X is an element of B minus C. Now, I don't know how this seems to you. You have to let me know. They can seem very tedious and very like, why do you have to do all that? But it is a really good exercise. It really helps you understand the ideas behind proofs, and it's just good for you. Okay, this one's a little different. This is not in chapter 8, but I thought we'd look at it. The empty set, which is the empty brackets or the null sign, is the set with no elements. And in some sense, I feel like it's defined by what it is not. It's the set with no elements. And sometimes proofs involving the empty set are done using a proof by contradiction. Now this is kind of a strange little proof, but let's try it. I'm going to use contradiction. So how do I proceed? Well, I have to negate my proposition, which says the empty set is a subset of every set. So maybe I need a little scratch work. That says for all sets X, empty set is a subset of X. So if I negate this, I am saying there exists a set X such that the empty set is not a subset of that set. So I'm going to start by saying this. Suppose not. Suppose there is a set X and the empty set is not a subset of X. That's how we begin. So now we have to remember, what does it mean if a set is not a subset of another set? So if this is not a subset of X, then there must be some little x in the empty set such that little x is not in uppercase X. But there are no elements in the empty set. So we have a contradiction. It's very strange. Okay, so mull that over. Now, proving two sets are equal can be a very tedious job, because what we have to do is we have to prove A is a subset of B, and then we have to prove B is a subset of A. So we use the techniques for proving subset relationships, only we have to do it twice. So we're going to do one of the distributive laws, which you probably never want to do again, but it's good practice, and one of De Morgan's laws, which is not so hard. All right, this is one of the distributive laws. Distributive laws. So proof. And you should draw a picture. We did this in chapter 1. So what am I going to do? First, I'm going to say, first we show that this set is a subset of this set, right? So we're going to pick an arbitrary element in this set and show that it's in this intersection. So how do I do that? I say let X be some element in A union B intersects C. Now, our book likes to use A instead of X. Sometimes I think A belongs to the set A, And so I like to use X, but it doesn't matter, whatever you want to use, just as long as you're consistent. Now, we're going to just use the definition. What does this tell me about X? Then X is in A, or X is in this intersection B and C. Okay, so we have to consider these two cases, but we don't have to say we're doing cases. I'm just going to say if X is in A, then what? Then X is in A union B, right? And X is in A union C. So, wrong color, X is an element of A union B intersect A union C. Now, if, on the other hand, if X is an element of this intersection, then what does that mean? X is in B and X is in C, right? If X is in the intersection, it's in both. In turn, this means X is in A union B and X is in A union C. Because if you're in B, you're in A union B. If you're in C, you're in A union C. So you see how this seems a very tedious argument. The picture is so much easier to use. But we have shown now that this set is a subset of this intersection here. Okay, so what did I do? Well, I said what it meant. X is either in A or X is in B and C. Then, if X is in A, I showed that that meant it was in that intersection. And then if X was in the other one, B and C, it was also in both of those two pieces, so it had to be in the intersection. So in either case, we got that subset. So now we have to go the other way. Next, we show that A union B intersect A union C is a subset of A union B and C. And we're going to need another page. Okay, so again, we're going to let X be some arbitrary element of this set. Okay, so we have to parse out what this means. Then X is in A union B and X is in A union C. Now, something I want to point out, you don't really need these parentheses here. I'm just doing it because when I'm writing on this tablet, it's a little tricky, and I like to have it be as clear as possible. Now, let's think about what we have to show for this X to belong to this union, it either has to be in A or in both B and C. So let's see how this is going to work out. Since X is in A union B, we have X is in A or X is in B. Also, since X is in A union C, we have, what do we have? X is in A or X is in C. Okay, now, if X is in A, then X is in A union B intersect C. Agreed? If X is not in A, then X is where? X is in B and X is in C. Now that might have seemed a little, hey, how did you do that? Well, let's look. X is in A or X is in B. X is in A or X is in C. If we take away this, if X is not in A, then X has to be in B. And again, if X is not in A, then X has to be in C. So that's a little, you have to think about it. But if X is not in A, then it has to be in B and it has to be in C. So if X is not in A, then X is in A union. Well, let me maybe say it one more step. Then X is in B intersect C, and so X is in A union B intersect C. Therefore, well, let's stop that. Let's say, thus, A union B intersect A union C is a subset of A union B intersect C. Now I can say therefore, because we've shown both directions. A union B, well, let's write it the way the proof is stated. Therefore, these two sets are equal. I told you probably never want to do this again. But it is a very good exercise. And my thing is messing up. It's a very good exercise to go through at least once. So you should do the homework and see if you can reason your way through it. Okay, we have to take a break.